I'm Lei, a research scientist at ByteDance. Today I'm going to talk about our recent work on improving our large language model training reliability at runtime. Today's large language model training jobs span tens of thousands of GPUs, often running for days or even weeks. At this scale, the system becomes extremely sensitive. Even small glitches can have outsized impact. Training efficiency is fragile. A single fault, whether hardware, software, or network related, can derail the entire job or silently waste compute. At the same time, reliability is both more difficult and more essential than ever. Issues are inevitable, but our observability is often too coarse or delayed to respond quickly. This creates a growing need for fast, automated systems that can detect and diagnose problems as they happen, not just after the fact. Let's now look at existing observability across model training, and we typically rely on to understand training health. We already have a wide range of signals: hardware metrics like GPU utilization and memory throughput, system counters like power and temperature, logs from CUDA, and profilers like PyTorch Profiler or Insight. But despite this wealth of data, observability in practice is still limited. First, the signals are noisy. Metrics vary naturally across workloads and machines, making it hard to know what's abnormal. No single metric is definitive because different faults manifest differently depending on the task and workload. What's worse, failures often propagate indirectly. A root cause on one machine might appear as symptoms somewhere else. Logs and traces are often coarse or delayed, missing necessary information to reveal the actual root cause or guiding the directions for debugging. And when issues do happen, manual diagnosis is slow, often requiring deep expertise and coordination across multiple teams. All of this points to the need for finer-grained, more targeted observability. In this talk, I'm going to introduce our solutions to leverage different fine-grained observabilities to improve reliability in our daily large language model training systems. First, I'll talk about how we leverage metrics for efficient and accurate debugging. Even though we have many collected metrics, using them may not be trivial. Let's take a look at an example of the PCIe downgrading and justify how such process is tricky. When the PCIe downgrading issue occurs at a receiver NIC, it causes the NIC to reduce its data transmission rate to the GPU. As a result, the NIC buffer quickly filled up, triggering the NIC to send more PFC signals to the transmitter side. Before the transmitter could adjust and slow down its transmission, the switch buffer became overwhelmed by in-flight packets, leading to an increase in ECN signals. Consequently, the CMP at the faulty NIC surged as well. This chain reaction led to a drop in NIC throughput, reduced the GPU utilization, and thus affecting the overall training performance. In this scenario, the root cause was the downgraded PCIe in a single NIC, but the issue propagated rapidly to other machines, causing multiple abnormal metrics to emerge. When system developers and operators try to debug the problem, it could be confusing to figure out the real root cause among all these problematic metrics. Through our analysis, we identified several challenges in designing an accurate faulty machine detection system. First, faults can occur across a wide range of areas, from intra-host computation to inter-host networks, and from hardware to software communication libraries. These faults are diverse in both type and proportion. When examining faults and their corresponding metrics, we observed that the same fault type can manifest as different anomalies in metrics. For instance, an ECC error might result in both high GPU and CPU utilization. Similarly, PCIe issues could lead to high GPU utilization or decreased NIC throughput. On the other way, the same metric anomaly does not always point to the same fault. For example, high GPU utilization could be associated with GPU hardware errors, GPU software errors, or even network issues. Besides, defining whether a behavior is an anomaly are actually task-dependent. For example, A GPU temperature of 7 degrees Celsius is considered abnormal when the GPU clock frequency is 1350 MHz, but it is normal for tasks where GPU operates at a higher clock frequency of 1800 MHz. The same principle applies to PFC rates. Additionally, we observed that metric data often contains noise caused by factors such as jitters, inaccurate sensors, temperature fluctuation, timestamp misalignment, and more. These inconsistencies can mislead the detection process, making it less reliable. We have seen it's not trivial to leverage those collected metrics to debug complex problems. Then let's think about how to utilize the correlations among those metrics. We first find that metrics across machines exhibit consistent behavior during parallel distributed training at per second observation window. When a failure occurs, such as PCIe downgrading, the PFC rate demonstrates distinctive differences compared to normal operation. This principle can be extended to other metrics, offering a potential pathway for systematically identifying faults. To denoise the time series data, you can leverage the notion of abnormal continuity. Once a fault occurs, abnormal performance typically persists across several consecutive windows per second. This can be used as a reliable indicator for identifying faulty machines and ruling out noises. To address task-dependent anomalies, we find that we can use individual models to represent each monitoring metric. Since the monitoring metrics are independent, each model and their respective metric data are utilized independently for both denoising and detection purposes. With those insights, we built Minder, a fault detection system for large language model training. Minder processes metric data from each time window and generates an alert when a faulty machine is detected. The design consists of two key components: constructing VAE-based parametric models for anomaly detection, and a similarity and continuity-based check to ensure accurate fault identification. To construct parametric models, because labeling task-dependent faults is challenging and may not be practical, we choose to use unsupervised learning. VAE is widely used for denoising and compressing high-dimensional features with strong reconstruction capabilities, and is proved to be an effective option in Minder. Various statisticals and machine learning techniques can be incorporated into VAE's encoder and decoder to capture temporal characteristics. In Minder, we employ LSTM as both encoder and decoder, given our data consists of temporal time series. LSTM is also shown suitable in our cases, as it considers both forward and backward information, enabling it to extract the complete correspondence information from the data. With the constructed parametric models, Minder achieves runtime detection that applies the concepts of machine-level similarity and continuity as from our insights. For each time window, Minder first pre-processes the raw data and uses a pre-trained model for reconstruction. It then compares the similarity among all machines by analyzing the z-score of the same metric. In the presence of a faulty machine, its z-score is significantly higher than a predefined threshold. Minder then shifts the time window and identifies machines that consistently exhibit anomalies across consecutive windows as faulty, thereby filtering out false alarms. One important thing here is the metric prioritization. Minder calculates the maximum z-score of a metric across all machines and maintains a decision tree on metric selection. Minder has been successfully deployed in ByteDance for the machine learning training tasks, monitoring tasks at a scale of over 1,000 machines. In our evaluation, Minder reduces detection time by 99% compared to previous manual diagnosis processes. We compared Minder with baseline outlier detection method, and it demonstrated Minder's performance by effectively detecting actual faults while maintaining a lower false alarm rate. This improvement is attributed to Minder's use of VAE for denoising and its ability to extract the data patterns for more accurate distance calculations. We analyzed the breakdown of fault types and found that Minder achieves an overall precision of 90%, effectively handling CPU and GPU related errors. From our detection results, we also discovered that models focusing on PFC, CPU, and GPU metrics are sufficient to address the majority of faults. We've so far seen how to leverage metrics to identify anomalies in large-scale training. Unfortunately, real-world bugs could be even complex, where metrics are not enough to expose problems. Now let's look at a different level of observability, which we found was previously missing but important: the collective communication library. Some of the most frustrating failures we see in large-scale training aren't crashes. They are gray failures. In these cases, the job slows down or even gets stuck. But none of the system metrics raise an obvious flag. Everything looks fine on dashboards, but the iteration rate drops, and the job silently wastes compute. Such gray failure can be from a single GPU's abnormal behaviors in collective communication, which can cascade to the entire job. Here's a concrete example that illustrates the blind spot we are up against. In this case, one GPU silently slowed down during an all-gather operation. There was no crash, no exception, but because collective operations are tightly coupled, all ranks are stuck. The job eventually failed, but only 10 minutes later when Nico timed out itself. When engineers look at the profiler output, logs showed no errors or traffic issues. Nothing pointed to the root cause. In the end, identifying the faulty GPU required manual testing and elimination, which is time-consuming. This kind of gray failure is especially dangerous because communication libraries today operate as a black box. There's no insight into how data flows, when a rank falls behind, or why communication gets stuck. Many tracing tools have been deployed across the stack to aid performance analysis and debugging. At the operation level, tools like Charka can capture its execution timelines and provide coarse-grained insights into training workloads. At the kernel level, frameworks such as Nsight and NPKit offer deeper instrumentation of CUDA kernel activity. Besides, at the RDMA layer, tools like Aegis provide visibility into low-level transport operations and packet flows. However, when collective communication problem occurs, these tools fall into many limitations. First, there is a granularity mismatch. Operation-level tools lack the resolution to capture sub-operation steps, while low-level tools offer overwhelming details which actually mislead the debugging process. Another concern is unreliability. Many tools are designed for offline testing, which is not suitable for runtime detection given their overhead and functionality. Lastly, most tools offer limited context for root cause analysis. They capture symptoms but do not aid in attributing the fault to a specific rank or component. We have seen that CCL-level information is necessary to construct the end-to-end observability and further expose important runtime information. But also we've discussed that achieving such observability at runtime is hard. Our idea is to review the dependencies, a key aspect for collective communication, and see how this can help our debugging process. We argue that we should think of the CCL as a system software, not just a library of functions. Especially for collective communication, we can think about the overall data transmission process as a global state machine. All GPUs move through stages to transmit and sync data in different parallelisms, which involves strong control and data dependencies. We conclude these dependencies at different levels. A collective operation at a single rank depends on GPU, CPU, and RDMA coordination, which involves tight control and data dependencies itself. Ranks in a group depend on each other for data synchronization, where downstream data transmission relies on completed upstream data coming in. Besides, operations like reduce getter itself involve both communication and computation, which can also involve further dependencies. Let's look at an example and see how those dependencies works at a slow all-gather operation across ranks. Nico splits data into chunks, and each rank will transmit chunks to the next one at each step. Since rank 0 is slower than all others, the first chunk arrives late at rank 1, which affects rank 1's next transmission to the following ranks. All ranks are then affected in this way. Since it's a collective communication, all runs are shown executing the operation slow. However, we can see that there's one single rank 0 to blame for such slowness. By identifying those dependencies, we can trace them at different levels. We first trace trunk level information, where we monitor how data transmission is achieved along an operation's execution. This includes how much data is copied and transmitted at runtime. On a different dimension, we track flow level information, where we observe how multiple network paths in parallel are transmitting data, which involves many channels and QPs at the same time. Tracing those dependencies can provide further observability on how collective communication executes across all GPUs. To understand what's the system state when a failure or performance problem occurs. With the idea of tracing dependencies in collective communication, we built Mycroft, a tracing system that achieves CCL-level observability and root cause analysis at runtime. We instrument the Nikos proxy thread to capture runtime information by tracking trunk movement through the communication path, including when data is copied, transmitted, and completed. Such instrumentation covers all network paths that achieve the data transmission. Mycroft generally collects two types of logs. Completion logs are generated at the end of each collective, summarizing metadata such as start and time, total data transferred, and NIC usage. State logs are emitted periodically during the operation, recording per component trunk progress, effectively producing a time-resolved view of the communication behavior, especially when the latency is longer than expected. We did some engineering optimizations to limit the runtime overhead, which is critical. All generated logs are written to pre-allocated memory space at runtime, which significantly reduces the overhead injected to the critical path. All data collection, uploading, and further analysis process are on the side of the main process. This enables Mycroft to gather runtime data at scale. Once data is collected, Mycroft is deployed in backend to consume all those data for detection and root cause analysis. A practical question is how to quickly detect problems among a large-scale cluster. Mycroft's triggering mechanism is based on the observation that with complex parallelisms, failures or performance problems can rapidly spread across all GPUs. Our experience is that such cascading is usually within a few seconds. Given this, only monitoring a subset of GPUs is enough to implement a proactive trigger and quickly identify a new problem. We check for many types of failures or performance issues and use this to determine that there are potential problems occurred in collective communication where we should analyze the root cause. Once an anomaly is triggered, Mycroft runs a lightweight dependency-driven root cause analysis. The logic varies based on the communication pattern. In ring-based operations, we compare how much data each rank transmitted. The rank with the least progress is often the source of the stack. We also look at the trunk level state to determine what type of problem has occurred. For example, if data was prepared but never transmitted, that likely points to a network fault. If everything was transmitted but GPU activity is stuck, that's likely a compute side issue, and we should figure out why the GPU didn't copy data. This gives operators not just a failure alert, but a localized root cause, including the rank and the likely direction of the deeper root causes. We implemented Mycroft as an always-on system that tracked ByteDance's daily training jobs. Mycroft is a lightweight system and can be deployed on a single machine that has only 64 CPUs. At runtime, Mycroft only requires less than 100 GB of memory to monitor all large-scale training tasks in our company. Despite this scale, the footprint on each host is minimal. Mycroft only involves limited CPU usage and 512 MB of fixed shared memory space allocated per container. This allows Mycroft to run with low overhead without affecting the training performance. Besides runtime overhead, we run a detailed evaluation to measure Mycroft's overhead in real training settings. Across a range of workloads, we found no observable differences in end-to-end training time between runs and with and without Mycroft enabled. These results make Mycroft practical to run as an always-on system, even at scale. As from our online experience, Minecraft makes no observable MFU difference for our online jobs. Instead of runtime deployment, we also conducted a series of fault injection experiments to verify Minecraft's ability. We injected various types of failures into training jobs, such as slowing down RDMA NICs, stalling GPU operations, blocking the Nico proxy thread, or congesting the network. These faults were introduced during collective operations in a small-scale testbed. The results were promising. Minecraft successfully detected all faults and correctly localized the root cause in all those cases. Here's an example. We simulated a NIC shutdown during the training. At runtime, we disabled the RDMA NIC on the GPU. Because Nico doesn't immediately crash in this case, the job just gets stuck as expected, with no clear errors in logs or profile output. Minecraft quickly picked up the anomaly. It noticed that a rank stopped sending prepared data through NIC, while others are also stuck with more data already transmitted. It correctly localized the problem to the problematic GPU and identified the NIC as the potential failing component while analyzing the observed system status on the GPU. This diagnosis was completed in just a few seconds, way before the job would have timed out. To wrap up, large language model training demands not just efficiency, but reliability at runtime. In this talk, we saw how traditional tools fall short. They are either too high-level or too heavy to help when failures silently propagate at runtime. Our solution was to effectively leverage different levels of observabilities, either utilizing them or instrumenting necessary trace points to collect meaningful runtime system states. We also emphasize our argument that CCL should not be operated as a black box, and we actually can observe it in lightweight methods. We believe that bringing system-level observability closer to machine learning infrastructure will be essential as training continues to scale or at different machine learning scenarios like inferencing, both to reduce waste and to improve robustness in production environments. We also believe that our work is just a starting point that opens the door to a broader set of techniques that can meaningfully advance long-term reliability in machine learning infrastructures. Thank you.